Okay, so we have so far been considering circuits where we have a voltage source. So we do some work and we imagine pulling charges off of one plate and putting them on the other, say, and therefore creating an electric field. And if we integrate the electric field over this distance, that's equivalent to a voltage difference. And so we have a voltage across this region. And we then, we will in a little bit notice that there's some energy there, and that energy can be released, as we've seen. There's some power, notion of power, and we released it through the existence of a resistor. So we put a resistor in the circuit and we got that energy out. But now we want to think of a way of keeping this energy in the circuit, and therefore we will have an object like this, something we call a capacitor, two little plates where you can have charge stored on them, and so that creates an electric field, or a localized electric field, and then we can have that energy transfer into a different form, into the form of a magnetic field. And here is a way of producing a localized magnetic field. That's just an inductor. We know that an inductor, in the limit of an infinitely long tube with current flowing around the tube, we get a magnetic field that's along the axis of the tube or solenoid, and zero magnetic field outside. Of course, we're not going to put in an infinitely long magnetic field, an infinitely long solenoid, but the magnetic field will essentially be weak outside and strong inside, in the same way that the electric field will be strong in this region and weak outside of the parallel plates. So this will allow us to keep energy in the system, and in order to explore this, we're going to call this an inductor, and the symbol for that is L, and we're going to call this a capacitor. And these are sort of intrinsic features of this solenoid that produces a magnetic field, and of this capacitor, which produces an electric field. And we will write the quantities that we care about in terms of the inductance and the capacitance. So the inductance is, for a given amount of current going through here, you'll get a certain magnetic flux through some region, and that's what we mean by the inductance. That's a feature of the actual object. That's a fixed feature of the actual object, and we want, our principles aren't changed. If we integrate all the way around the circuit, we'll get that this quantity is zero. Now there's some subtlety here in that there's actually time dependence, and so in reality there are, this is not the result of a static electric field, but the non-static electric field, if you will cause charged particles to move around. And so if we only take into account the charged particles that produce a sort of diverging electric field, this will hold up, but there is some subtlety there that we need to take into account. We won't worry about the details here. This expression is still valid for the electric field produced by charged particles, and this just means that the voltage difference all the way around is zero, so we need the voltage across here and across here to impose this condition. So we know how to get voltage from flux, right? It's the time derivative of this quantity, so this is equal to L times I, and so d phi by dt is equal to, L is just a constant feature of the object, the solenoid. So this looks like that. And the EMF is minus. Right, so that's all we need is the voltage across an inductor, and it's this kind of an object. And for practical purposes, the reason why we have inductors is so to avoid jumps in current. Let's think about the capacitor, right? So the capacitance of the capacitor is just for a given amount of charge that you store on the plates, you'll have a certain voltage across there, right? You create an electric field, and the integral of that electric field over that distance is the voltage, up to a minus sign. And that's what the capacitance is. And so the voltage, V, is that. So we have these two quantities which will need to come into play in the equation that applies this condition. So now we're going to think of the energy that's stored in the inductor and in the capacitor, and that's what we'll do next.